Welcome to NPTEL online course on fractal and multifractals. In the last lecture, we have discussed the compact and its property. How to say given set as a compact and its property we have discussed in the last class. So, in this class, we will define what is a Cauchy sequence, and then we will define what is complete metric space and contraction mappings. Up to this we will discuss in these lectures. So, let me start with the Cauchy sequence. So, a sequence xn in a metric space x comma d is called a Cauchy sequence if for every epsilon greater than 0 there exists a n naught belongs to n such that the distance between xn and xm must be less than epsilon whenever that n and m are greater than or equal to n naught. So, here you can observe that for every epsilon greater than 0, if there exists a stage n naught such that after the stage n naught here, if you are finding the distance between 2 points, then it is always less than epsilon. Say for example, suppose if you have the space like this one, this is your metric space, then here consider the sequences like this one, these are all the sequences points here. Now, for every epsilon greater than 0, there exists a state, n naught, say for example, after this n naught, if you are finding distance between any two points in the sequence, then it is lies less than the epsilon. The distance between the 2 point after this state is less than epsilon. So, in the Cauchy sequence, it does not allows that too much variation after certain stage. The points are not moving here and there in the random manner, that the distance is uniform after certain step n naught. Let me give some example of the Cauchy sequence. Take a metric space R with the Euclidean metric. The sequence xn is defined by 1 upon 2 power n is a Cauchy sequence. Here for every epsilon greater than 0, there exists a n naught such that the distance between xn and xm is less than epsilon for all n and m greater than or equal to n naught. So, this sequence is an example for a Cauchy sequence in the real numbers. Now, instead of the real number, you can take the rational numbers. In the x with d is a metric space, when we already discussed that if A is a subset of x with respect to the same metric, then this A comma d forms the metric space. Here we take modulus of x minus y as the metric with respect to the same metric, this q form the metric space. So, this we mention here as the d of x comma y equal to modulus of x minus y. Consider the sequence xn defined by the decimal approximation of square root of 2. That means x1 equal to 1, x2 equal to 1.4, x3 equal to 1.41, x4 equal to 1.414 and so on. This sequence is Cauchy sequence in Q because for every epsilon greater than 0, there exists a state n such that after certain state the distance between the xn and xm less than epsilon in this sequence. So, here this two sequence xn 1 by 2 power n, and here it is defined as the decimal approximation of square root of 2, both will forms the Cauchy sequence. Now, every convergent sequence in a metric space is a Cauchy sequence. Every convergent sequence in a metric space is a Cauchy sequence. Fine. For proving this one, let take xn be a convergent sequence and it has the limit. That limit we can call it as x. That means limit n tends to infinity, xn approaches to x. That means we can take xn as a convergent sequence and its limit is x. Now, we need to prove that this convergent sequence xn is a Cauchy sequence. Given epsilon greater than 0, we can choose n naught belongs to n such that the distance between xn and x less than epsilon by 2 for all n greater than or equal to n naught. This is true. Why? Xn is a convergent sequence. If xn is a convergent sequence, for given epsilon greater than 0, one can find the n naught some stage. After this stage, if you are finding any point in the sequence xn, the distance between xn and the limit x is always less than the epsilon. So, if one can find some epsilon, then obviously one can find other epsilon, then you can choose appropriate n, then this sequence also, this inequality is still true. Then after this, then if n and m greater than or equal to n naught, that means after the stage n naught, one can choose two state n and m. Then distance between xn and xm, use the triangle inequality here. If you are using the triangle inequality, we have xn and xm. In between and xn and x1, we can choose some intermediator anywhere. If you are choosing the intermediator, find the distance between xn and xm and find the distance between xm and x. If you are adding this one, it is obviously greater than the distance between xn and xm. We know that after the stage n naught, if you are choosing any state n, the distance between the 2 points is epsilon by 2. So, here n and m both are greater than or equal to n naught. Therefore, this term, the first term is epsilon by 2 and the second term is epsilon by 2. This is less than epsilon by 2 and this term is also less than epsilon by 2. Therefore, one can get epsilon. So, after certain said n naught, the distance between any 2 points is less than epsilon. So, we assume that the given sequence is convergent sequence and proved that the sequence is a Cauchy sequence. Now, you can see here every sequence in a metric space is a Cauchy sequence. Then what about the converse? Whether every Cauchy sequence in a metric space is convergence, that we need to verify. For that, consider the metric space, the rational number system with the standard metric, and consider the sequence xn as the floor function of n times root 2 over n. Here the root is this n over 1 by n, it is in the form of, because the numerator is always an integer, the floor function n and root 2 is always an integer, it is belongs to integer, and the denominator also an integer. So, that n start from 1 to infinity, this n value is n belongs to n. So, the numerator and denominator both are integer. So, it is in the form of p by q. Therefore, this this sequence in Q. So, you can consider this sequence. Clearly, this sequence converges to root 2. So, how this sequence is convergent to root 2? We can prove it. Let us see what is the floor function. The floor function is greatest integer function, that means a number which is greatest integer which is less than or equal to the given number. Now, if you are finding the floor function for this one, then one can get root 2 is less than n plus root 2 plus 1 or greater than or equal to n floor of n times root 2. It will satisfy this property. Now, both the side, if you are dividing by n, that all the side if you are dividing n, one can get 1 by root 2 of n less than or equal to root 2 less than n root 2 plus 1 by n. If you are, this sequence is a given sequence, so x n less than or equal to root 2 less than x n minus 1 by n. If you are subtract with all the number by x n, then you can get 0 less than or equal to root 2 minus x n, which is less than this plus, this is 1 by n. So, when n tends to infinity, this lower bound is 0. When n tends to infinity, this sequence we already seen, this sequence converges to 0. Therefore, this sequence must convergence to root 2, that means root 2 minus x n, if n tends to infinity, it must be 0. Therefore, the x n converges to root 2 whenever n tends to infinity. Therefore, this sequence converges to the number root 2. Using theorem 3, one can show that x n is a Cauchy sequence, because if the sequence is convergence in a metric space, the sequence is a Cauchy sequence. This sequence is a Cauchy sequence. However, it limits root 2 is an irrational number. So, the point root 2, the limit of the sequence does not belongs to rational number. So, it means that there exists a Cauchy sequence in Q which is not converging into the space. So, because the limit of this sequence is root 2, therefore, it is not convergence in the metric space Q with the Euclidean matrix. Now, let us discuss some propositions which will be applied in the upcoming results. Let x n be a sequence in a metric space x comma d, and the distance between x n and x n plus 1 is less than 1 by 2 power n for all n, then x n is a Cauchy sequence. So, for proving this one, let x n be a sequence in a metric space, and let take epsilon greater than 0 and choose n naught such that this n naught 1 over 2 power n naught minus 1 less than epsilon. Then for all n greater than m and greater than or equal to n naught, one can get distance between x n and x n. This we can write because n is greater than m. So, it has x m and x m plus 1 up to x m minus 1 m plus n minus 1 and x m plus n, this term. If you are finding distance between x m and x n, then using the triangle inequality, one can obtain this result. Then we assume that the distance between xn and xm n plus 1 is less than 1 over 2 power n. So, here in the each term the distance between two pair of element is 1 over 2 power n. There are 1 over 2 power k m, where k runnings over m to n minus 1, there are n minus 1 times previous terms. Now, this is less than or equal to, this is the finite series that we can extend up to the infinite number. So, k equal to m to infinity 1 by 2 power k. So, which is equal to 1 over 2 power m minus 1. Now, that instead of n, one can take n naught, then which is less than or equal to 1 over 2 power n naught minus 1, which is less than epsilon we already choose. So, finally, we have the distance between any two pair of element after certain stage n naught is less than epsilon for all m and n. Therefore, xn is a Cauchy sequence. So, xn is a Cauchy sequence. So, we have seen that in a metric space, if you are taking the convergent sequence, it is a Cauchy sequence, whereas the converse is not true. That means, we cannot say that every Cauchy sequence is convergent. Now, we need a space, we need a metric space such that if you are taking any Cauchy sequence in the metric space, that should be convergence. This leads to define the metric space, that is called the complete metric space. A metric space x comma d is said to be complete if every Cauchy sequence in x converges to the element in x. For example, R with the standard metric or Euclidean metric is a example of a complete metric space, and similarly R2 with D is a complete metric space with respect to the Euclidean matrix, where the points are taken x1, y1 and x2, x1, x2 and y1, y2. The distance between these 2 points x1 minus y1 power 2 plus x2 minus y2 power 2, take the power of 1 by 2. This forms the complete metric space. That means, this matrix makes R2 as a complete metric space. Similarly, the set of all continuous function defined on the interval 0, 1 forms the complete metric space with respect to the uniform matrix, which we are defined in the previous lectures. That means, the supremum between the distance between two functions at the point, which forms the complete metric space. These are all the example of the complete metric space. Now, let me define what is the contraction mapping. A self mapping F on the metric space x comma d is called a contraction mapping if there exists a constant or there exists a exponent epsilon belongs to closed interval 0 and open 1. That means, the alpha value is greater than or equal to 0, which is strictly less than 1, such that the distance between the images of x and y is less than or equal to alpha times the distance between x and y for all the values of x and y in x. Then this mapping F is called the contraction mapping. The ratio alpha is called the contraction factor or contraction ratio. Now, what is the geometrical meaning of this contraction mapping? Say, for example, if you have the metric space like this one and it is a self map, we have the other metric space, same metric space, this is the x, this is also x, the F is a mapping from x to x. So, if you are taking any 2 point in the metric space or in x, here 2 points if you are taking x and y, and find their images. This is f of y and this may be f of x. Then find the distance between x and y. If find the distance between x and y and find the distance between the image of x and image of y here. If the distance between these images is lesser than the alpha time the distance between the images of x and y, then we can call this mapping as a contraction mapping. That means the distance between x and y, we are multiplying with the ratio alpha. So, this distance is less than or equal to this, means the distance between the points means this 2 point is, if you are taking this set, if you are applying this function, then this function contract the, that means it is compress this set into here, just compression from here to here. Fine. Let me give the example of the contractions. F from the real number system to real number is defined as f of x equal to x by 2 on R. For all x y belongs to R, we need to show that this function is a contraction mapping. The function is defined as f of x equal to x by 2. To prove this for the contraction, find the distance between f of x and f of y. So, f of x and f of y can be written as x by 2 minus y by 2. We take the modulus because we are taking the usual matrix. Then if you are taking 1 by 2 out, then 1 by 2 times x minus y. If you are taking alpha is 1 by 2, then the distance between this one is less than or equal to alpha times the distance between x and y. Therefore, we can say f is a contraction mapping on the space R. So, what is the image of this R with respect to this function f? This function, maybe we can take this set, instead of the R we can set this set 0 and 1. If you define the function f from 0 comma 1 to 0 comma 1, the function f of x is defined as x by 2. What it does, it makes, if you apply any point in 0 comma 1, then it will be reduced to by half. So, 0 will map to 0 and 1 will map to the point 1 by 2. So, the image of this function, image of this set under this function is, one can take 0 comma 1 by 2. That means, the interval 0 comma 1 is reduced to 0 comma 1 by 2. That means, there is this function under this mapping f, this set is compressed to this one. Now, you can see this is the reduced size of this one with the ratio alpha. Suppose instead of x by 2, if one can take x by 3 as a function, this function f of x equal to x by 2, instead of x by 2 if you are taking x by 3, so you apply this function on this domain, then one can get 0 to 1 by 3. So, again under this mapping the set 0 comma 1 is mapped to the set 0 comma 1 by 3. That means, this function f reduced the set in the 0 comma 1 by 3 in the ratio of alpha. So, if with respect to the alpha, if you are choosing the alpha appropriately, accordingly this function will act on the set and it will reduce the size of the original set. So, what is the use of the contraction mapping? as we know, we need to define fractal in a mathematical way. We say that the fractal means it has the self similar property. If you take any part of the object, it will reflect the whole. Now we are in the process of constructing the fractals in metric space. So for constructing the fractals, we have to take the object and we need to reduce it. For reduced it, otherwise we need to take the object. If you are taking any part of the object, it should resemble the same. So if you apply the contraction mapping on one set, then this function reduced the originality of this set into smaller copies. Then it will help us to construct the fractal in a metric space. Then I will stop here. These are all the few references one can read and get more knowledge into the foundations. Then we will discuss in the next class. Thank you.